Burcu from Max Planck Institute, and she's going to talk to us about trace-aware random testing of distributed systems.
Thanks for the introduction. I'm Burcu, and I'll talk about our work on trace-aware random system of distributed systems. Distributed systems are intrinsically complex systems, and it's hard to reason about possible executions of them. It consists of a number of nodes, which process a number of concurrent client transactions, and while doing that, they coordinate and synchronize each other by exchanging asynchronous messages. So the non-determinism in the order of asynchronous messages, non-deterministic node failures, and their reboots at unexpected times may result in some subtle bugs which only expose only in certain orderings of certain events. And as the name of that session implies, our high-level goal at detecting those bugs is testing. Ideally, we would like to test all possible executions of a system. However, this is infeasible. Consider an extreme case if we have all events concurrent to each other, n number of them, then we would have n factorial number of possible executions. Practically, what is being done is random testing, which in general comes with no guarantees. Last year at UPSA, we presented a randomized testing algorithm which comes with some probabilistic guarantees on the lower bound of hitting a bug. And it was based on bounding the sample set by some bug depth. And now, in this work, we incorporate partial order reduction techniques and bring trace awareness together with depth bounding. And we present trace-aware randomized algorithm, which comes with better probabilistic guarantees. I'll start with an overview of PCT on a very simple example. Now, in that example, we have two nodes, and initially, message A is sent to node 2, and concurrently, message 1 is sent to node 1. Whenever node 1 processes message 1, it sends message 2 to itself, and it does this for a chain of n events, and finally, after message n, it sends message B to node 2. Now you will notice message A and message B are actually concurrent to each other, meaning they could be executed in any order. And let's say that the program is buggy, the execution is buggy, if message B happens to execute before message A. Random walk algorithm, which is a naive algorithm which decides which event to schedule next, uniformly at random among the enabled set of events, detects this bug with a very low probability. At the first step, it decides between message A and message 1, and it goes with message 1 with 1/2 probability. And again, in the second step, it chooses between A and 2, and so on for n number of choices. And the probability of hitting that bug will be exponentially low in the number of events n. PCT's guarantee on the guaranteed probabilistic bound is based on two factors: online chain partitioning and parameterization by bug depth. PCT stands for probabilistic concurrency testing, and with chain partitioning. For simplicity, from now on, I will use PCT. During the execution, PCT decomposes the events into totally ordered chains of events with respect to their causal dependencies. So in that execution, we actually have two chains. One is message A, and message 1 to message B are causally dependent on each other, and this is chain 2. And then we assign random priorities to chains. Let's say that priority of chain 1 is greater than priority of chain 2. Then this means that we're scheduling the events in chain 2 and then scheduling the events in chain 1, which gives us that trace, which is correct. But if the priority of chain 2 is larger, then we would schedule these events in chain 1, chain 2 earlier, which would hit the bug. Now you will see that PCT hits the bug with only 1/2 probability. And this bound is based on bug depth. Bug depth is roughly the minimal number of ordering constraints between the events. If we're considering the ordering between two events, then we can capture some problems like order violation, just like the one we've seen earlier between message A and B. if we're considering ordering requirements between 3 events, let's say E1 and E3 supposed to execute atomically, but E2 interleaves in between them, there is some atomicity violation, then we can capture this with that number of ordering constraints. And as we increase the ordering constraints, we can cover more complicated bugs. PCT samples from a bounded set of schedules, which is parameterized with respect to the bug depth D. And as we increase bug depth D, we sample from an exponentially larger set of schedules. And at the boundary, if the depth equals n, then we can capture all executions. Our sample set covering depth D executions is strong D-hitting family of schedules. Very simply, a schedule strongly hits a tuple of events, E1 to ED, if it schedules those events as late as possible in the execution and preserving their order in the tuple. And in a strong D-hitting family, it's such a set of schedules such that for each D tuple, we have a schedule which strongly hits it. PCT samples from that family of schedules by sampling actually a tuple of them. Let's say it samples E1 to ED. E1 is strongly hit, meaning it is executed as late as possible because it is in the smallest priority chain. We saw already, we assigned some initial priorities. And we strongly hit the left D-1 events by reducing the priority of a chain at the event to a lower one. And the sample set consequently is number of chains times the permutations of D-1 events chosen from n events. So we've seen this depth bounding sampling. An orthogonal approach is trace-aware random sampling, which applies partial order reductions into testing. So let's say that in the set of schedules I'm sampling from, for a schedule, there are a lot of equivalent schedules, but for some of them it is unique or there are less number of them. And I'm testing the system, running it many times. If it happens that many of the schedules I tested are actually equivalent to each other, it's not that useful. We would like to cover a diverse set of behaviors as possible since our testing times are limited. Partial order reduction techniques aim to reduce the sample set to explore by pruning out equivalence schedules, pruning out the redundant executions. And the equivalence is defined based on the dependence relation. Two events in a distributed system are dependent if they are causally dependent, meaning that execution of one of them gives rise to the execution of the other. Like I'm executing an event and this causes me to send another message to some node, or the receiver of these two nodes are the same, meaning that in different execution orders of those events actually result in a different state. So these orderings capture the certain behavior of the system based on the ordering of the events which are dependent to each other. And two schedules which only reorder independent events are equivalent. So let's see here, dependence relation induces equivalence classes, traces of schedules, and our ideal goal is to sample from traces, but not from individual schedules. Notice that this is orthogonal to what we already saw, depth-bounded sample set, which was constraining the sample set by bounding, but this time we are pruning the equivalences. On another example, I will show you that PCT is not trace-aware. And in that example, we have 3 nodes and 3 initial concurrent messages. Message A sent to node 1, which gives rise to message B to send to node 1. Message C sent to node 2, and when it's processed, message D is sent to node 2, and message E sent to node 1, which gives rise to message F. And let's say the execution is buggy if message E, executed in node 1, interleaves with the execution of message A and B. Now this time we have a more complicated bug, and strong hitting 2 events will detect the bug. Strong hitting E and B will schedule them as late as possible. So message A will be executed before them. And we want these orders to be preserved. So let's see how PCT strongly hits that tuple. We start with online chain partitioning. And we have 3 chains this time, 3 chains of causally related events. And let's say we have initial random priorities such that C1 greater than chain 2 and greater than chain 3. Now, in the previous example, the requirement ordering we were looking for was only 1 between 2 events. But this time, we are looking for more number of orderings. So in addition to initial priorities, we also need to sample D-1 priority change points where to reduce the priority. And here are the possibilities. So I can change the priority of the chain at message A, meaning that before executing message A, I reduce the priority so that I continue with the events in chain 2, like CD, and then move to chain 3 and execute A and B. Or I can change the priority at B, meaning I strongly hit message B. So in each schedule, the bold message is the one which is strongly hit. In this case, message A will be executed, then the priority will be reduced. So I go on, drain the events in chain 2 and 3, and then execute message B, and so on. So these are the possible executions. And you will see only one of them hits the bug. And if we consider the orderings of message A, E, and B, actually some of the schedules are equivalent to each other. But PCT doesn't care. It just strongly hits an event chosen from the available set of events. Now, what we're trying to do is exploiting partial order reduction techniques. Let's see what are the dependence relations in our example. In our example, message A and E, both concurrent and being processed on the same node, are dependent to each other. Similarly, the orderings of message B and E will give rise to different executions because they are also dependent and co-enabled, which we also call RACE. But for instance, the orderings between message C and E, we don't care because they are independent. And if we look at the traces, which are obtained by the orderings of this dependent on co-enabled events, A, B, and E, we actually only have 3 traces, where a high number of schedules fall into the third trace. Now, our goal is to characterize our sample set so that we will eliminate sampling from the redundant executions. In trace-aware PCT, we again have our chain partitioning, but where trace awareness comes into play is the selection of those D-1 priority change points. We select which events to strongly hit by considering the dependence relation between them. So briefly, what we want to do is we strongly hit an event if reducing the priority at that point will give me a different trace, which would be entailed by the default chain priorities. So for instance, if I change the priority at A or B, then changing the priority of A will cause message E to go before B, which will give me a different trace. But if I change the priority at C, that wouldn't give me a different trace. So here, if we could carefully select these D-1 events from these out of race events, then we will see that we actually prune out some schedules which would be sampled by strongly hitting messages C, D, or F. And I would only sample from these traces. Now the sample set is reduced such that, again, we strongly hit one of the events with 1 over number of chains probability. But we this time select these D-1 events not from whole set of schedules, but only these race events whose orderings would matter. Most related work to our work are partial order sampling, POST, and PCT. So POST, as the name implies, is a trace-aware algorithm. And it is also a priority-based algorithm, but it assigns priorities to individual events, samples a permutation of those events, considering the dependence between them. The guaranteed probability with this algorithm is exponentially low in N. And this is not a surprise, because as we discuss in the paper, an online algorithm where the events are revealed online during the execution cannot guarantee a probability any better than an exponentially lower one. So this is actually theoretically what can be obtained. And how PCT obtains it exponentially only in number of parameter depth is because it focuses on a smaller set of sample size. So since for a given depth of D, we have a better probability of hitting a bug here, I will put an arrow here. In that work, we aim to bring together trace awareness and depth bounding by adding this trace awareness into PCT algorithm and presented taPCT. Similar to PCT, taPCT utilized chain partitioning, but this time we were sampling from n hat number of events instead of n number of events. So we have a better guarantee here. One could bring together these two goals optionally by adding depth bounding to partial order sampling provided by POS. Actually, in our paper, we also present that algorithm. In that algorithm, we don't have chain partitioning. So again, we're giving priorities to individual events. And we're again sampling from strong D-hitting family. We're hitting some D events. But this time, we have this guaranteed probability 1 over not number of chains times n to the power of d, but max con comes as a parameter, which is the maximum number of events concurrently enabled with another event. It turns out that DPOS is a specific case of taPCT where the chain size is 1. This has a lower guarantee, so taPCT is stronger in the sense that it strongly hits not only the smallest priority event, but a chain of events. And finally, between DPOS and PCT, there is no clear winner because that depends on the execution parameters. There's an interplay between max Kong and number of chains and the amount of race events, non-race events in the execution, and depending on the program structure, nature, they can have varying performances. In our paper, you will see that we evaluate different execution parameters and the effect of those parameters for all these algorithms on a simple akka micro benchmark. Together with the micro benchmark, we evaluated our algorithms on 2 real-world systems, Zookeeper and Cassandra. Here I present the results for Cassandra. The columns show the sampling algorithm, the number of traces sampled out of 1,000 iterations, and minimum, maximum, and the standard deviation of the frequency of hitting a certain trace. Now, the first 3 algorithms, random walk, another baseline algorithm, RAPOS, and POS are just mentioned, are the algorithms which sample from all executions. And you will see that they sample kind of diverse traces, but none of them hits the bug here. By the way, the bug in that case we're looking for is a bug where the nodes concurrently process 3 client transactions, and the bug occurs if some of the nodes receive some of the messages of a transaction interleaving with the messages of another transactions. It has more than 50 number of events with a huge sample set of executions, and all these algorithms sampling from all executions cannot detect the bug in 1,000 executions. And depth-bounded sets of sampling from depth-bounded set with the algorithms DPOS, PCT, and taPCT can focus on the executions more likely to have the bug in a better way. And you'll see both DPOS and PCT can detect the bug, but taPCT is more successful at exposing the bug. I would like to conclude with a brief summary of taPCT algorithm. So as we said, it brings together this depth bounding, focusing the sample of sets to depth bounded set of schedules, and also partial order reduction, eliminating equivalent schedules, and sampling from a smaller set of schedules. And it guarantees, guarantees to hit the bug with a probability of at least 1 over number of chains times number of race events to the power of d minus 1, where the number of chains represent the concurrency in the system, and hat represents the dependence between the events, and d is the bug depth parameter. Thanks for your attention, and I'll be happy to answer any questions.
Okay, I think we have time for maybe one quick question. If our next speaker could be setting up while that's happening, that would be great. Any questions? Can I see everyone? Okay, I have a slightly random question.
Random.
This is slightly outside my area, but John Hughes has done a lot of work on quick check, obviously.
Quick check.
So another random testing approach. And he had this intuition that says you should actually generate really, really long. So rather than sort of doing a depth-bounded exploration, you should generate really long test cases because they have more subsequences, right? So is there any corresponding sort of intuition behind your work, or is that just totally off the wall?
Quick check, as far as I know, quick check addresses input non-determinism, and where we're addressing mostly concurrency non-determinism. We assume transactions are given, and then we look for the interleavings. And for concurrency non-determinism, the intuition is a bit different. So the intuition is that any concurrency bug would expose in small number of interleavings. So we could minimize it in a way that the bug can be replayed with a smaller number of interactions. That is the intuition behind bug depth. But again, the bug depth in distributed systems is still larger than the bug depth in multi-threaded programs. So it's mostly called like deep bugs.
Okay, thank you. Right, let's thank our speaker again.